Yeah, hope we are live. I think so. Hey guys, good evening. So Navneet here. I'm the lead organizer for TFUG Coimbatore, and hope you are staying safe and taking care of yourself, and hopefully vaccinated too. So in this COVID situation, we need to take care of ourselves and maintain social distance. So that is our responsibility. And like after a long time, we are doing a session through TFUG Coimbatore. It's been a while, so a lot of things have happened in the past, and we did TF everywhere Tamil Nadu last month, I think. So today we are excited to come up with a new series of advanced TensorFlow sessions. Hope this interests you, and hopefully share the. So we are on YouTube Live. Share the links to your friends and your colleagues. So a lot of cool stuffs are ahead, and we have an awesome speaker today. But before getting into the session, I would like to just give an introduction about the communities and the things that we are doing here. So TensorFlow is about Coimbatore. I think you should be familiar with that. We started back in Jan 2020, and it's an one and a half years travel and been done 10 plus events. Through TFUGs, like we do organize tech talks, webinars, and mentorship, and also support few hackathons and stuff and all. And there are a lot of TF communities available. I'll just explain for you to know the ecosystem and stuff. So the first is TensorFlow communities. We have TensorFlow user groups, MLGDs, and special interest groups and ML working groups. So these are the groups supported and kind of maintained by Google itself, and we get a lot of support in terms of speaker and sponsorship and education content and stuff and all. So in that, TFUG is a community, and it's a group of developer, engineers, researchers, and students. Basically, a like-minded people joining together to share and exchange their knowledge. And it's a completely free, open source, community-driven learning initiative. So we are present in 70 plus, 15 plus countries, and we are about 70 plus. But this is just the old stat. I think we are 100 plus groups right now around the world, and MLGD is the next set of open source education from Google. So GDEs are Google developer experts. They work closely with Googlers, and they do tech talks, meetups, and online webinars, and they educate people on AI, machine learning, and TensorFlow technologies. And next, we have special interest groups. This is a group of people, mostly Googlers and people associated with them, like GDs and TFUG organizers. They take a specific set of problem and work on that. And there are a lot of special interest group available. I know TensorFlow started as a library, and now it is a full-blown framework. So we have TF Lite, TF Extended, TF Mobile, TF Microcontroller, and TF cloud and web. So a lot of things are there, and special interest groups kind of focus on these niche areas and specific areas to build solutions and build open source tutorials on that. And the next is mobile ML working groups. Currently, ML working group on or available for mobile on ML on mobile OS, ML on JavaScript, and explainable AI and diversity and inclusion working group. And again, it's a collaborative initiative from the core developers from Google, and also MLGDs and TPG organizers. So what we focus on in TensorFlow through education, we focus on helping people to use these TensorFlow tools in their projects, okay, and also in real-time production pipelines. And there are TensorFlow core products like TF library, the Keras, the core TF library itself, and TFJS, TF Lite, and TF Extended, and other supporting tools like TensorBoard and JAX, and deployable solutions where you can do edge deployment using TPUs, and cloud deployment using GCP, and also development platform Collab. So we discuss on all sort of concepts in machine learning, but like little bit of focused on TensorFlow as well, like computer vision, object detection, and NLP, and ML in general. In India, we are about 14 chapters, I think. I guess we should be plus or minus two, there are more groups added in the past few months. We are in 14 major cities, mostly Chennai, Bangalore, Coimbatore, Hyderabad, and New Delhi, and most of the cities. I think all of these communities are active, and they've been doing webinars and what to say, tech talks and mentorship up to their level. Okay, so mostly we are advised to have 1 month per one event per month. So we are keeping up with the pace. So yeah, if anyone living away from Coimbatore, or you are a part of another city, you can become a member of these meetup groups. And Tensorflow Tamil Nadu again is one among big event we have done it last month, and we got awesome speakers from the world, and you showed extensive support to us. And it's the video is still on YouTube. You can go and watch it back if you need to gain some insights on that. And this event is completely organized in Tamil language. Okay, so we are going local these days. We are organizing more events in Tamil language to address the native speakers, native listeners, and native audience. So why communities? What do we do actually is communities are a great place to learn things. Okay, so especially in this 2020 21st century, things are moving in the rapid pace, right? So it's very hard for us to keep up with all the technological creations and inventions, and every day new library come out. It's really hard for us to keep the pace. So communities help us in learning, sharing, and getting feedbacks from the peer learners, and also do some open source implementations, collaborate, network, and get hired, and also get recognition. So in the past 2 years, I personally believe we have impacted more than 10K students, and it had created job opportunities, meeting new people. It's kind of shown them a new way to pursue a career in AI. So that is what we have achieved. I firmly believe that. So again, this is what I've already told. So communities are a place for like-minded people to share and exchange knowledge. In Coimbatore, we have AI Coimbatore and TFUG Coimbatore. We are officially on Meetup. So Meetup is our official group. So once you become a member of our Meetup group, all the events and all the stuffs will be notified to you. Once we create the event, we will personally reach out to you, and we are planning for a lot of events in the coming days. So please join our Meetup group. So you can just Google it, TFUG Coimbatore, and the first link it will take you to the Meetup page. And again, it's not only for the speakers, and it's not only for the organizers. Even you can become the speakers. And you can collaborate. You can contribute in terms of organizing a meetup, in terms of sharing your knowledge, in terms of mentorship, and creating content for our meetups and events. So yeah, we are open to have anyone who is willing to contribute and share their knowledge. It might be technical or non-technical. You can put your efforts to drive this open education. So do join our community. We are AI Coimbatore and TFUG. So apart from Meetup, we also have personal groups, close knit groups. We are a 500 member group on WhatsApp with 2 channels, and we are also on Telegram. Daily conversations, daily news update, question and answering sessions happens in our group. If you are interested, you can reach out to us on our Meetup platform. And these are all some of our events. Yeah, COVID has changed our life, especially. So we used to have a lot of physical meetup. We meet people and we build stuffs. But due to COVID, for the past 1 year, we are doing mostly online events. But these are some of the pics from our previous events. So again, members from these groups, if you're watching, hopefully we will successfully come out of this pandemic and meet people in person, and exchange knowledge. And anyone can join. This is not limited to engineers, developers. To be frank, like, we even have a 12-year-old kid in our group, and we also have 50 plus, 60 plus PhD scholars who are guiding us in learning new stuff and helping each other. So these are all some of our volunteer and core team members. You can become a part of this team. So they help us in organizing events, and this is our mentor team. So we are helping people in learning AI and to pursue a career in AI. And myself and my team is here. We are leading the communities, and if you want to contribute, please reach out to us. You can find us on online. And without any ado, we'll get to the today's session, building high FPS object detection pipeline with NVIDIA Deepstream and Triton by Akash James. So Akash is a well-known personality on LinkedIn. He used to post cool demos. I've been following him for quite a long time, like maybe 6 months or so. His lot of his demos and his education materials are awesome, and he's too kind, and he's also very open to collaborate and educate people through his YouTube channel and his blogs and GitHub. And about Akash, Akash is an AI architect and at Integration Visa. He's also NVIDIA Jetson AI ambassador, and even I'm excited to looking forward to Akash session. And yeah, I'll Akash is here. Akash, thank you for accepting the invite and being a part of our community. So it's over to you. You can take over the session.
Thanks, Nivu. So, hey everyone. I hope you're excited and you want to pretty much learn how to build the kind of pipelines that I keep usually posting, right? So the whole idea is to share knowledge, and I hope you can have a couple of great takeaways from this. Also, side note, I have a lot of cats, so please don't get distracted by the one that's there, and then you might see a couple of them walking around. So let's get started. Um, I guess most of you are familiar with AI and the kind of developments that have been happening in AI, right? So I think computer vision has caught a lot of drift, and computer vision
Yeah.
is
Hi,
being used
Akash.
widely.
Akash, sorry to interrupt. This is Navneet. So your voice is going high and low. It's caused because of your mic. So you can uh, have your mic steady and yeah. Okay.
Sure, is it perfect now?
Yeah, it's perfect now. But like, you were moving your head, so that's why there's highs and lows in the audio.
Oh, okay, that way. All right. Okay,
Okay.
so all right, I'll keep that in mind. Right. So I was saying that computer vision has pretty much caught a lot of drift, and it is being used widely in the industry, right? So um, I think if you take examples from a couple of years back, getting accuracy was a big deal, right? And fast forward today, I think there are several models and papers out there that kind of get you really good, accurate results from neural networks and different algorithms. And I think we're in the age of performance. It's all about being able to scale on multiple input sources and on smaller devices. So these are my 2 cents on that. And I believe if you really want to scale on devices, NVIDIA is the way to go. So they are, I think, the largest GPU manufacturers, and they really support the deep learning community, right? I mean, they have some amazing packages out there that we can use, and two of them are Deepstream and Triton. So, let's go back to the basics, right? So, what exactly is object detection? Just to, make sure that all of us are on the same page. Um, Object detection is simple. It's all about detecting different entities in input data, where your input data, are images, and you tend to detect these objects, you classify what exactly they are, and you localize them, right? You kind of tell where exactly they are in an image. So this is an output from a popular algorithm called YOLO. And you can see that YOLO is capable of detecting people and buses and trucks and bags and whatnot. So it's trained on Coco dataset, which is by Microsoft, and it's one of the state of the art models, right? It has really good accuracy and is capable of detecting objects, whether they're small or whether they're big or occluded and so on. So uh, I think the first breakthrough was classification, where we were able to tell what the primary entity in an image was. And obviously the next step was to localize it, right? Because an image can consist of your entity as well as other pixels that do not belong to your entity, which is noise. So in this case, a cat, and the cat has a background of grass. So you ideally want to localize where your object is. The next obvious thing was, what if you have multiple objects in your image? You ideally want to detect them, and you can have dominant objects in your image, or you can have not so dominant objects in your image. So here you can see the example of a dog and a couple of kittens and a rubber duck. So uh, that's where object detection is. It's pretty accurate. The next step is segmentation, where you want to get exact definitions of your object. But we're going to stick with object detection for this webinar. Now, I'm pretty sure a lot of you have built your detection pipelines, right? You've probably run YOLO v4. You want to detect people, you want to detect vehicles, you want to detect weapons, and several different objects out there. I have seen some really creative work with object detection. Uh, but if I had to summarize the common pipelines out there, it would be something like this, right? You decode an input source. OpenCV is one of the most widely used packages for this. You might be using video capture, and you kind of decode the input source, or maybe just read an image. Um, you perform inference with your models. The frameworks that are most popular are TensorFlow and PyTorch. If you're an avid YOLO fan, then it also might be Darknet. But most models are trained with these frameworks, right? So you run inference with them as well. You might write a couple of logic blocks. Once you get your detections, let's say you detect a vehicle and you want to count the number of vehicles that you detect. So you might have a small logic block where you keep incrementing a counter based on the number of vehicles you detect. And then finally, you want to display this data, or you might want to push this data on a cloud service. It can be maybe a self-hosted Apache Kafka, or it could be something like AWS Greengrass, or Azure IoT services, right? So that's typically how I would summarize a pipeline out there. Now, there are several flaws with this pipeline. Apart from the inference, nothing else is accelerated. You pretty much decode your sources on the CPU. Then you push this decoded information into the GPU for inference. You pull out this inference information from the GPU to the CPU scope. You run your logic, and you also display on screen using your CPU. So inherently, CPUs are not really good at doing this. CPUs are the jack of all trades, right? I mean, they can do everything, but they're not really fast for graphics. That's where GPUs come into place. But in typical workflows, the only thing that is accelerated on a GPU is your inference, and that is where the primary bottleneck lies. Now, how do we get rid of this bottleneck, right? How do you accelerate your workflow? So that's pretty much from the title of the webinar, right? So you have some amazing tools out there for acceleration, and I'm pretty much going to focus on Deepstream. So Deepstream is this framework that kind of combines different SDKs and acceleration libraries that NVIDIA provides, like Cuda, TensorRT, CudaNN, and so on, right? What if you could accelerate the pieces of pipeline that I showed earlier, and you could accelerate everything using a GPU? That way, all of your bottlenecks would be gone, and you could run multiple streams uh, in parallel, right? So, of course, today people are able to get real-time performance on a single stream, maybe two, maybe four. But how do you really scale this to larger numbers like 32 streams or 64 streams? Now, let's just see how Deepstream would handle the same kind of a problem. Uh, Drawing parallels to the previous architecture that I showed you, the regular workflow, here you would decode your input stream using the various multimedia APIs that NVIDIA provides. You pre-process your data with Cuda. So your pre-processing could be, for example, you want to resize your image, you want to flip it, you want to rotate it, and all of that good stuff, right? There are various kind of pre-processing steps that you might want to do, and here all of it is GPU accelerated. The next thing, you might want to track, or you might want to perform inference on your image. You might want to perform inference with multiple object detectors on your image at the same time. So your one object detector might be detecting vehicles, another object detector might be detecting weapons, and ideally you want to stack them together and perform inference. Tracking, I think one a major issue that most people come across is tracking your objects, right? So of course you detect a person in one frame, and you detect the same person in the other frame, but of course regular object detectors do not have the intelligence to track the same object, right? And ideally performing tracking on CPU is slow, if especially if you're performing tracking by analyzing the pixels. So you can imagine, right, an image is 1920 times 1080 in size, and you can multiply it by 3 again for RGB, and that many data points exist in an image, and if you try to track per pixel, that is an expensive operation on a CPU. So Deepstream kind of also provides accelerated trackers on the GPU, and all of this can be stacked together. There are times when you want to classify your specific object, right? So maybe you're detecting cars and you want to tell if that car is an SUV, or if it's a sedan, or if it's a hatchback. So you might train a classifier, and then how do you plug in the classifier into your existing pipeline? So you might crop the image, you might feed it to your classifier, get a result. Not very efficient, right? Because your cropping is happening on CPU level, and again you're going to push this image on the GPU. So there's a lot of bottleneck involved when you try to create complex pipelines. Here with TensorRT and Cuda, you can do all of this together on the CPU or on the GPU, right? Everything is parallel in nature, and it is extremely accelerated. How it is accelerated, I'll show you in a couple of slides further down the line. The next step, ideally, you want to show again comparing parallel. I mean, drawing parallels to the previous pipeline. You want to show this information on the screen, and you might want to send this metadata onto a cloud service, or probably use that metadata in some form, right? So Deepstream also provides plugins that directly interface with popular cloud services and queue services. So breaking it down even further, this is an example of how you would perform inference on an RTSP source. So in case you are not aware, CCTV cameras generate something called an RTSP feed, or rather you can connect to the camera's feed over a protocol called RTSP. So in a typical Deepstream pipeline, the capture process, which is initiating the communication with the camera, because it's a network camera, and doing the authentication and kind of getting the rights to that camera, is performed by the CPU, because it is a network operation, and CPUs are brilliant at that. The next step is to decode your information, right? So typically NVIDIA GPUs have something called a decoder, an NV decoder and an NV encoder. So these decoders help you decode the information from RTSP streams into a specific format that you might require. So again, in the previous pipeline, you kind of decode your input using OpenCV, and your output is basically a NumPy array. So in this case, it is something similar, but something more compatible with a GPU. Again, the next step is image processing. Here, Deepstream kind of gives you the opportunity to decode, perform the image processing on a GPU or on a VIC or an ISP, right? So again, focus is on the GPU. When you kind of perform pre-processing steps on the GPU, it is much more faster. Fast forward, batching. The management of batching happens on the CPU, but of course, batching itself happens on the GPU. Your detection and classification are performed by deep neural networks, again, a GPU, or certain NVIDIA devices have something called a deep learning accelerator, also known as DLA. You can use either of these things, and perform your inference. So a DLA is comparable to a TPU that Google provides. Next step, tracking. Of course, you could track on the CPU or GPU based on your liking. So Deepstream kind of provides you multiple trackers. Visualization. Again, when you want to draw on an image, right, and you're essentially running at 30 frames per second, or if you're running at scale, you might have thousands of frames per second that you might want to draw on. So that is taken care by your GPU as well. Finally, your display and storage, right? I mean, pretty simple. You display with your HDMI, and you store on your SATA storage or your SSDs and so on. So now you might think that there are so many pieces and puzzles here, right, that you might have to work on these individual things altogether. The beauty of Deepstream is that all of this is kind of connected, and they give you something called plugins, and all you have to do is just stack the plugins one after the other in the form of a graph and kind of get the output. So I'll show you in further slides. So I think at the heart of Deepstream lies TensorRT, right? Because the slowest operation in your object detection pipeline is the object detector itself. If you are using a very large object detector like YOLO V4 or FasterRCNN, typically the frame rates are low. If you're running on on an entry level GPU or on a mid range GPU, the FPS is pretty low. You might get something like 5 FPS, 10 FPS. YOLO, yes, you might get 30, 35 FPS, but not very scalable, right? So that's where TensorRT kind of comes into picture, and the support that TensorRT has is actually pretty crazy. It supports all the frameworks out there which you might be using to train. And the best part is TensorFlow and PyTorch actually have integrated TensorRT in them. Apart from that, Paddle not very widely used. MXNet and Cafe definitely they are some of the frameworks that were widely used at least a couple of years back. You could convert these into something called an ONNX format, which is an open neural network representation, right? It is like the mediator form where you could convert between the formats. So again, if you use TensorFlow, there's TensorRT integrated. If you're using PyTorch, there's a version that's compatible with TensorRT. If you're using anything else, you can just follow some simple steps and convert your model into an ONNX format. Now, what next? So TensorRT provides APIs that helps you convert your graphs or your models into an engine file. So TensorRT creates something called an engine, and these packages kind of help you. TensorRT provides APIs that helps you convert from one form to the other. Now, again, the question that might arise, Akash, I might have to learn TensorRT for this, and it's pretty complex. Converting it to an engine file is not very simple. So Deepstream also takes care of that for you. They have bindings where you can directly give weight files, and it automatically converts, or maybe you can give it an ONNX file and it automatically creates the engine for you. So what exactly does TensorRT do? Once you've trained your neural network, again with any platform that you prefer, there are pretty much 5 things that TensorRT can do with your engine file. I'll start with the first one, which is the most common thing out there. It is precision calibration. So we train with FP32 precision, right? And maybe if you're into medical or deep learning, you're probably using FP64 or something that's really big. Ideally, if you want to perform inference, you don't really need that kind of precision. That kind of precision is necessary while training, but when you're performing inference, in most cases you don't need it. So TensorRT gives you these amazing APIs that helps you convert from FP32 to FP16 or from FP32 to int8 quantization. And especially when you do int8 quantization, you get some amazing speeds. Also, in a little bit of insight, FP16 kind of uses your tensor cores, right? So it kind of makes full use of the tensor cores on the GPUs that you have. The next thing is layer and tensor fusion. So Of course, you have multiple layers in your neural network, right? Probably the most basic template out there is a convolution max pooling, right? So uh, what TensorRT does is, over the years, TensorRT has slowly gained the ability to kind of combine different kind of layers and tensor outputs, intermediate tensor outputs together, and make the operation faster. So if you have designed neural networks or played around with the inputs and outputs, you know that a tensor is nothing but a matrix, right? It is a vector representation or a matrix, and GPUs do nothing but matrix operations. If you can combine these matrices in a different way, where the number of operations that the GPU has to do is lower, but your output is the same, then obviously your inference is going to be faster. So that's what TensorRT does, and especially with popular layers out there, uh, uh, they have kind of achieved this kind of speed up. And of course, if you are a researcher and you have worked on your own kind of layers and custom neural networks, you can write the APIs to convert your specific model to an accelerated form in TensorRT. So TensorRT also has a version called the open source version, TensorRT OSS, and you could build that and still get the performance that NVIDIA gives, plus the performance that you might have figured out as a researcher or as an avid tinkerer. Dynamic tensor memory, right? So when you load something on a GPU, like any other memory, you need to clear the memory once you're done. Again, this is really difficult to do when you're interacting with a GPU on a low level, right? So TensorRT kind of handles that for you. So when you perform inference, when you push new data, it makes space for it. It uses those memory blocks. Once you're done utilizing the data, it clears it for you. I mean, it just makes your life a little more simpler and allows you to focus on the true aspect of deep learning, which is the neural networks itself. Multi-stream execution. So I'm not sure if many of you have tried this, but if you load one neural network on your GPU, you might get X performance. When you load another neural network on your GPU, your performance divides by 2, given that they are the same neural network. So typically, frameworks like TensorFlow and PyTorch, they don't have this inference capability of having parallel streams together. But that's where TensorRT comes in. It kind of handles the number of models and the number of batches you're trying to process, and it makes it parallel in nature so that you can keep onboarding different streams on, and don't really get a very big performance penalty. Finally, we have kernel auto tuning. So you do know that GPUs have kernels, right? So here basically TensorRT kind of does an optimization for you. So kind of getting every last bit of performance that you can get from your neural network. And finally, you end up with an optimized inference engine after doing all of this. So it is a different representation of your GPU, of your model, and it is based on your specific GPU. So when you create an engine file, it actually identifies what kind of GPU you're using and how to accelerate for that specific model. So I mean, TensorRT is kind of designed to get you every ounce of performance that you can. Now, I did speak about plugins, right? So I did say that Deepstream has different plugins that you can keep stacking over one another to get your pipeline, and each plugin has its specific uh, task, or its specific operation, right? So on the left here, you can see that's a sample GStreamer pipeline that I have created. Of course, it is nothing fancy and it doesn't have object detection, but to probably give you an idea of how exactly GStreamer works. The first plugin you see here is URI decode bin. So that's where you specify, your input source. As I showed earlier in that architecture, you need to kind of specify your input source, right? So that's where you specify your input source. Also, URI decode bin has the capability of decoding your input source as well. Here my input source is an mpeg4 file. So it kind of employs plugins that are needed to decode mp4 files, and decodes this information and passes it to the next plugin. So the next plugin is NV Video Convert. This is a plugin given by NVIDIA where it's decoding and kind of converting this information on the GPU based on certain parameters that you might have given. I have not given any specific parameters here, nothing fancy, just regular stuff. You have video rate followed by a couple of parameters. So you do see that I've specified the width as 1920, height as 1080, and frame rate as 10 FPS, right? So that's where your conversion is happening. I'm kind of reducing the input source from 30 FPS to 10 FPS. I'm converting that output using Video Convert plugin, and I'm displaying it using something called Auto Video Sync. So on the right, you can see that it pretty much plays the output. So that's how simple GStreamer is. Actually, you just need to know what individual plugin does, what kind of input it accepts, and what kind of output it gives, and you can construct your pipeline. Now, to go a little bit into detail of how GStreamer actually works, right? So on the left, uh, uh, a plugin has an input and an output, right? So it takes in some kind of data and it outputs another form of data by performing some operations on it. Now, what Deepstream exactly does is it gives you certain plugins that are accelerated on the GPU. So you have a low-level API that GStreamer provides, and that communicates with your GPU, right? So let's say you want to decode your MP4 file, and you want to reduce its size. So if this plugin is responsible for converting the size, it's going to take the input as your image, kind of push it on the GPU, and convert it and give you back the output, right? That's how a plugin typically works. Now, again, I'm sure all of you have written modular code, right? Everyone loves writing modular code, and you divide functions, and your individual functions perform a specific task. So think of plugins as your functions, right? And you call these functions in a specific order to get your desired output. So in the same way, if you see the image on the right, you have multiple plugins and you kind of connect them together. So a plugin has a sync pad and a source pad, SINK and SRC. You connect a source to a sync and so on. So the data that's at the source goes into the sync of a plugin. And these are nothing but the input and output pads of a plugin, right? That's basically where you get the input and push out the output, and you just need to make sure that these pads are linked to each other and the plugins are compatible with each other. So you can't really just plug in anything you like, right? Obviously, if you have like 10 functions and they are supposed to be called in a specific order, if you mess up the order, your specific function might be expecting input of a specific kind, so you will have a logical error in that case, right? Similarly here, you can it's important to link the right kind of plugins together. Now you make when you collect similar kind of plugins and make it into a bin, or if you take plugins that perform a specific task and you put it together, it's called a bin, basically bin. So think of bin as a class, right? In very layman terms, it's you might have a specific class that you have designed where you perform certain kind of operations, right? So let's say you have a class called preprocessor, and you might have different operations in that, like you might define a function called rotate, you might define a function called flip, and so on. So similarly here, when you kind of collect plugins that are responsible for a specific task, you put them together and you call it a bin. Now again, I think this is one of the most important parts, right? So you do have a pipeline, and the pipeline has an asynchronizing agent. So the control has to be moved from one plugin to the other. So again, when you write your own algorithms in Python, for example, you might call the functions in a specific order. And you're the one who's controlling the flow of data, right? You define that kind of data. So similarly here, you have a synchronizing agent, and that kind of makes sure that data moves from one plugin to the other in your pipeline, and also that there isn't an overflow or underflow of data. So the example here is you have a video file and you decode it. So you can club these two plugins as the source bin. the example I gave, right? You might want to perform scaling, and you might want to filter your input. So you can collect these kind of plugins together as a process bin, and finally you display your output. That can be the sync bin. So that's the overview of how GStreamer exactly works, and the architecture of GStreamer. Now, I did mention Triton Server, right? So um, there are instances where uh, uh, you know going through TensorRT, or maybe just plugging in models directly into Deepstream, it can be a little bit tedious. So you have this a server called Triton Server, which uses gRPC or HTTP based on your liking, and you can deploy any kind of model inside this server. So your server can run on the CPU or on the GPU. Your models can be OpenVINO compatible, they can be Onyx models, they can be TensorRT as well, uh, maybe the TensorFlow or PyTorch, right? So you could theoretically also skip the entire TensorRT step, and or maybe if your models are not exactly compatible directly in Deepstream, but you still want to run performance at its best, you could use Triton Server in that case. So that's pretty much the overview, right? So uh, 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 now uh, I guess I think the final thing is to show how the code runs in action. I'll quickly go through the source code. Of course, the team will share the GitHub link for it later on, so that you can go through it. But probably I think I should just go through it once, so that you do understand, and I can of course run a demo for you to see. So let me just quickly change my screen. Okay, Nivu, just making sure my screen is visible, right?
Yeah, sure.
All right. Okay, so this is a sample application that I've written. It's basically it's written in C++. So the main focus has been performance, and there are certain aspects of Python which are not really fast. So I tend to incline for C++, but of course there are packages of Deepstream that are compatible with Python. So it completely depends on your flavor. But of course, if you want absolute performance, you would go with the a C++. Um, Again, pretty simple actually. I'll just take you through the main function that I've kind of created here. It's just a sample,
Akash, sorry to interrupt. You can zoom in a bit so that people can look into the code.
of course.
Yeah, yeah, enough, enough. Thank you.
All right. So um, I'm going to give references to the architecture that I've shown so that it makes sense. GStreamer, kind of gives you this amazing, structure called GST element, and you can kind of define different pointers with that. And of course, I'm sorry if some of you don't like pointers, but C++ is like that. So I guess using pointers is the way to go. Um, I've kind of initialized a pipeline element, a stream marks, a sync for my display, a tracker, which here is NV tracker, a YOLO detector, a converter for my to convert the format, OSD is on screen display, and Tyler is basically to kind of combine my output together and show it on the screen, right? um so I did show a terminal version of a GStreamer, right, where you can actually pretty much give a terminal command, something like this. Yeah, so you can give a terminal command like this, and it would pretty much start your pipeline. But this is the C++ version. It gives you more control over it. Same package, but you can define the stacking of your plugins here. Um, just to quickly glance through it, you have a pipeline. I created a streammux with NV streammux. I'm checking if these plugins are created, or it pretty much errors out. If they are not, I'm creating the input sources. So you remember that a source bin consists of plugins that are responsible for reading the input source and also decoding it. So create input source is just a simple a function that I've written that kind of does that for you. It reads all the source files that I'm trying to perform inference on, and it creates the respective bins. This function kind of returns the number of sources that I have. So the whole idea of doing that is uh, as I said, TensorRT is very parallel in nature. So you can set a batch size for your inference engine. So theoretically, you can run YOLO v4 at batch size 4, batch size 8. That is, it would perform inference on 8 images at the same time, right? But there is a point of diminishing returns. You can't just keep increasing your batch size indefinitely and keep getting a lot of performance. So based on the GPU that I have today for the demonstration, which is an RTX 2060, I've kind of theoretically found that batch size 4 is the best. So here, simple piece of code that if batch size is less than 4, the batch size can be the number of sources itself, which is 1, 2, and 3. If it's anything more than that, you just go with batch size 4. Now here I'm pretty much creating the primary GPU inference engine, or I'm using the NVInfer plugin that Deepstream kind of provides, and creating a detector out of it. Next thing, I'm creating a tracker, I'm creating the tiler, I'm creating the video converter. Again, I've commented this code, so you should have access to it later on after this presentation, and you can go through it. I created an OSD. There's some amount of code which is for Tegra platform. So Tegra platform is NVIDIA's Jetson devices. They are ARM-based, ARM-based devices, and there are certain pieces of code that are different. But of course, I've handled that here for you. Now, finally, you have to link all these things together, right? As I said, you need to stack all of these plugins together in a specific order. So this is where I do the stacking. Streammux is the plugin that's responsible for multiplexing different amount of inputs into your single batch, right? So that's the first plugin here. The second plugin is the detector itself. So after you're done batching, the information is fed into the detector, right? The next plugin is tracker. So once you are done, once your engine is done detecting and it has given you the output that these are the objects, you can start tracking them with the NV tracker. Next, you have tiler. So what tiler does is, let's say you're running 8 sources together. So you can tile these sources next to each other so that the output looks a little clean and it is easy to understand. You have a video converter. So up to this point, everything is happening on the GPU. So the converter actually converts the format from NV12 to RGB. So NV12 format is used by the GPU because it is more efficient. But RGB is necessary for drawing on the screen. So we convert it to RGB format. Then next, NVOSD is used to draw on the screen, right? So you've got your detections. Maybe you want to write some text. Maybe you want to change the color of your detections, and all of that good stuff that OpenCV provides. You can do most of it with NVOSD. And finally, the type of display you want. So you can directly write to a file, or you can show it on the screen, or you can create an RTSP stream that can be that can be viewed on a network. Or maybe you're not interested in the output at all. Maybe it's just you're happy with your pipeline and it's running in production. In production, nobody really needs to see the output, right? So we don't really put, in that case, the sync, the kind of sync that we put is called a fake sync, and that kind of gives you that small amount of performance increase because you're not really doing any display operation. finally it starts playing, right? I mean, that's pretty much it. The other functions are with more respect to linking the plugins together and making sure that everything is fine. So these functions are something that you don't really touch, but they're well documented, so you can definitely go through them. So let me just quickly run this example, right? I think that would be the most interesting part. Currently, I have 8 input sources. So I have a file called input sources.txt from which I read the input source. So I have a couple of videos here under the folder of YOLO demo. And there are 8 sources. So let's just see how 8 sources perform with this. Right. So here you can see that 8 sources of running YOLO v4 are present on the screen, and you can also see that the FPS per stream is actually pretty high. It's processing at 67, 68-ish FPS, right? So this is something that you get when you run completely on your GPU. If I were to show you the GPU output of how my GPU is currently doing, so that's the kind of performance that I'm getting. So currently my GPU is at 85% utilization, and the RAM, the VRAM usage is quite low compared to how other frameworks kind of load your models and deal with it, right? So I'm only using about 1800 MB currently, and I have a lot to spare. So which means I could theoretically load more models and stack them together and not see that much of a performance difference. Of course, I ran 8, right? But you want to see how far you can take it. So let me just double the number and let's go with 16. Okay, so I have restarted the application with 16 streams this time. And you can see with 16 streams it's still a pretty high FPS. We're still processing at about 40 frames per second, and it actually increased at this point, but yeah, it's fluctuating. So that's how easily you can scale with Deepstream, right? You don't really have to write code or do too much of work to kind of make production level pipelines. All you have to do is focus on the logic that you're trying to write and uh, the neural networks themselves. So you can focus on accuracy and the deep learning aspect of your pipeline. I think I should be able to run 32 as well. Not pretty sure, but let's give it a shot. I think it should on this device. Oh, great. So actually it's scaled up to 32 streams at this point, and I think they're giving about 20 FPS as an output. So that's around how much, 600 frames per second approximately. So that's again just to show how well a Deepstream scales with the kind of workload that you give. And if you just check my GPU at this point, I'm using 3.5 GB, and the utilization surprisingly is the same, right? So that's how a TensorRT kind of scales on your GPU, and of course Deepstream with all the other goodness of decoding and whatnot. So it kind of scales on your GPU and gives you the best performance that you can get. So here I can still keep adding streams and still kind of remain in the real-time territory without giving up too much performance. And of course this is an RTX 2060, so if you were to deploy on a much bigger card, you get higher performance. And if you've seen from my LinkedIn posts, I've pretty much hit numbers which are above 1000 frames per second. So that's YOLO v4. And if you were to truly master Deepstream, this is the kind of output that you can get. So this is something that we work on from an organizational perspective. And this is YOLO v5. It's running 32 streams again. The FPS is much higher. If you remember, the YOLO v4 was giving me 20 for 32 streams, but here I'm getting 30 frames per second per stream. And of course the output is just beautiful, right? I can pretty much expand whichever window I want, and view it. And you can also see tracker IDs being kind of being allocated to each object here. So that's how Deepstream and Triton can work for you. um I guess we can open up for questions at this point.
Yeah. Thanks a lot,
So
Akash.
hi. Okay, Surya, continue.
Yeah, yeah, it was a wonderful session, and going through the entire pipeline from getting the video to getting the final output was really awesome, and able to see so many videos done parallelly was really a wonderful use case. So there are a lot of questions, and we can take it up one by one.
Yeah, before
Navneet, would
that,
you
I
like to
have
add
few
something?
questions to ask. Yeah, yeah. Yeah, thank you, Akash. That was cool demo. And I have dozens of questions, but I'll limit it to three to four. Hopefully,
Okay.
most of the audience would have the same questions. So the first thing is how TF Lite is different from TensorRT and PyTorch Mobile. Like all these framework providers, they have an optimized optimization toolkit for their own language or frameworks. Okay, how it is different from this TensorRT Deepstream and all.
Oh, I think that's a really great question, right? So, PyTorch has something called Torch script, and as you said, TensorFlow has TF-Lite, and I think TF-Lite is also amazing when it comes to deploying on mobile devices, right? You want to bring AI to, or you want to bring computer vision to your devices, and that's where you kind of use TF-Lite. So the kind of difference that I would see is that TF Lite is amazing at making your models smaller, but that does not restrict you from not using TensorRT. Right? You make your model smaller, you optimize it with TF Lite, and then you can also move to TensorRT. So, uh, TensorFlow, you have used this framework to train your model, right? So of course there are a lot of optimizations that you can do to your model itself right during
Mhm.
training or after training with TF Lite. Now you want to now, since NVIDIA kind of is the GPU provider, it makes sense to use Tensor RT to kind of accelerate it further. If you are using Google based technology, which is I think you have the Coral dev board and you have
Yeah.
TPUs, right? So in that case TF Lite makes more sense. So but of course today NVIDIA GPUs are used the most, right? So you have to kind of make a decision on what you're trying to do. So my focus was to go with that cloud based deployment where you have like hundreds of cameras and you have like several GPUs also available with you, and you want to scale on the entire thing. But my recommendation would be to use TF Lite if you're building an application on your phone, an Android device. You're trying to create an application where you're performing object detection or classification. In that case, go with TF Lite. Or if you're using a TPU or a Coral board, uh, TF Lite is better in that case.
Right. Okay. Thank you, Akash. So again, I have a couple of questions, but before that, I'll just give a short note to the audience. So a session actually been scheduled till 7:30. So we'll stay for another 15 plus minutes. Hope so. You can drop your questions into the chat box. We'll pull them on the screen, and hopefully we'll make sure every question is being answered by Akash. Okay. Great. So without that, like second question is OpenVINO, I think hopefully you would have used it. What's your thoughts on OpenVINO? They run on Intel graphics, and how does it is like how different or how same it is to TensorRT?
So again, I haven't worked that extensively with OpenVINO compared to how much I
Okay.
have with NVIDIA tools, but I do have a fair idea on it, right? So there are some accelerated models with OpenVINO, and the beauty of it is that you can actually run it on the CPU, right? So when you don't really have large loads and you don't have a GPU with you, an NVIDIA GPU to be specific, because Intel doesn't really make that powerful GPUs out. at least not yet, right?
Mhm.
So but OpenVINO has an amazing community. They have a lot of support in terms of models, right? I mean, you have a lot of different kind of object detectors, pose estimation, classifiers. I mean, they're stacked. So uh, uh, again, so when you don't really have a device to kind of showcase or kind of run on a GPU, right? OpenVINO is the way to go. And uh, uh, I think amongst college folks and also organizations that are trying to make devices really cheap, OpenVINO is a hit because not everyone has an NVIDIA GPU, right? It's slowly
Mhm.
changing. People are buying gaming laptops, so gaming laptops have your NVIDIA GPUs and you can use it. But in case you don't have it, and you still want to work with AI, the perfect combination would be using Google Colab and OpenVINO. That's like the way to go. So
Okay,
I guess
great.
in terms of similarity, it's again very similar. The optimizations are different because they are developed by different
Mhm.
organizations and different set of open source people. But I think the ideology is the same.
Mhm. Okay, thank you, Akash. And the next question would be so when it comes to optimizing models for mobile devices, so there have been like from the TF tutorial, I got to know certain things. The first thing is like doing model level optimization. One is quantization or pruning. And third, it comes to the architecture selection. Okay, so hopefully you have run YOLO and SSD. Mostly it's fully connet based network, but there is also RCNN, fast RCNN. But fast RCNN is a different case. It's faster, close to YOLO. But when you take RCNN, there is a concept for region proposal networks and selective search systems and all. So again, the speed depends on the architecture choice as well. Any thoughts on that?
Yes, absolutely. I guess your speed definitely depends on the kind of architecture that you have, right? So I think the
And also the
RCNN
number of
family,
class.
the number of classes, it's very subjective. I think that would fall under quantization and pruning parameters. But if you
Okay.
just, let's say you are strictly with the initial performance you get after training your model, you're not doing any optimization. Let's just stay right after training. uh, yes, definitely the depth of your architecture really matters, and the kind of layers also it has matters, because obviously you're performing more operations, right? So uh, every you can kind of calculate the amount of operations your neural network is going to perform, and you can kind of classify it into ops, right? So there are like YOLO. Let's go into NLP, right? So NLP is huge. You have like BERT models which have like 340 million parameters, and at the same time in object detection, when you want to detect a face with retina face, it has just 2 million parameters or something. I may probably lesser than that. So definitely this has to be considered. And uh, 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 I suggest when you're going to production and into performance, just going with what everyone uses doesn't make sense. You have to see what kind of output you desire, and based on that select the neural network you want. In some cases YOLO might be too heavy. You don't really have to detect a person like very far away, right? You might want to only detect a person inside a room. So in that case, like as you said, SSD models are faster. So those kind of decisions have to be made.
Okay, great. Thank you. Great insights. And apart from these object detections and convolution operations, okay, all these OpenCV, like the classic computer vision technique, even they can be accelerated through Deepstream or
Absolutely. So yes, this is the kind of questions that I really appreciate. So uh, as I said, a plugin, right? A plugin performs a specific task, and NVIDIA has given certain plugins for you to use out of the box. You don't have to code them. You just take it, write one line of code, and it comes into your pipeline, right? But what if you want to do custom operations? NVIDIA is giving you batching, inference, and all of that. Maybe you want to maybe you want to do a specific operation to your image. Let's say you want to do edge detection, or you want to do a perspective transformation, right? So all
Mhm.
OpenCV operations, a stack of operations, you might want to first
Yeah.
convert it to black and white, then binary, and all of that stuff, right? So you can actually create your own plugin that does all of this. So as I said, consider a
And
plugin
particularly,
like a function.
yeah, sorry to interrupt, particularly image
Mhm.
stitching. So that is where we are working. So if you give some insights on that, maybe I can learn something out of that.
Yeah, sure, right. So when you're designing a plugin, inside your plugin you can write whatever code you want.
Okay.
As I was giving an example of just edge detection and all of that, right? So you write that code. If you want to perform image stitching, yes, you have your multiple images, you'll have some algorithm to match where to stitch it, and you'll do all of that, right? uh,
Mm.
uh, you do this, you package it into a plugin, you define what kind of input it is going to give, you define the output that it's going to give, and you plug it into your existing pipeline. So let's say your plugin now needs to go into the sync plugin of that Deepstream gives, right? So it is expecting output in a specific format. Just make sure that your output after you're done all your operations are in that specific format so you can display it. In case that is not possible, go ahead and define your own sync plugin. Just take the code, which is open source, change the parameters accordingly, and define it. So the thing is, this also promotes reusability. You can take, once you have defined this plugin, you can just use it
Mm.
anywhere in any other code that you want without having to worry about too much of porting and all of that. And the best part is OpenCV actually has CUDA acceleration. So like blurring, right? For example, so if you're using Gaussian blur, you also have an equivalent called Gaussian kernel, which is CUDA accelerated. So
Yeah.
now essentially what you can do is, again, you can write OpenCV code also that runs on the GPU, and everything else is running on the GPU. So that's just pure speed that you get out of your pipeline.
Mm. Okay, okay. Thank you, Akash. So with that, I'm done, and I have one last question, but maybe you can answer that at the end of the session. If
Okay.
someone wanted to get into this NVIDIA, and of course, a lot of drones and autonomous systems, they need onboard computing, right? So if someone wanted to learn these stuffs, what resources you would recommend, and if you have any tutorials, you can you can share it with us. Maybe you can answer that question at the end, like what you need to know before you jumping into it, because without knowing neural network, if you jump into optimizing neural network, that doesn't work, I think, right?
That's true.
So
That's very
you can
true.
kind of give a roadmap to become an expert in edge computing, so that you can answer in the end. And without that, any due, we'll take some question from the audience. Okay. Surya, you want to happen?
Yeah, I can take care of this one. So thanks a lot, and I hope many people learned a lot from Navneet's questions. So let me get to the others audience question. So this is one of the questions that I also had. So Akash, can you see it on the screen?
Yeah, absolutely. So will quantization using TensorRT
Yes, sir.
degrade the performance of the mode?
Yeah,
Uh, I'm assuming the mode you're saying is Int8 and FP16.
yeah.
So
It's talking about the quantization.
right.
Yes.
If you're going from FP32 to FP16, the kind of drop in performance is very minimal. If you're going from FP32 to Int8, uh, you have to do something called a calibration graph. So I think, and I think that's the place where most people struggle, right? So I think I'll take it from the top. So now you want to train a model. Uh, you have trained in FP32. Now there are post level optimizations that you can do if you have already trained your model. If you're going to FP16, TensorRT does it directly for you. You can go from FP32 to FP16 without any code changes, and you will see a slight reduction in performance. You can go from FP32 to Int8 by creating a calibration graph. So what this calibration graph does is, in layman terms, it is basically scaling your FP32 values and your Int8 values, right? So that you get similar performance. Of course, there is a drop in accuracy at this stage, right? So something like YOLO v4, if you were to do Int8 quantization, you may not notice the drop in accuracy because the YOLO v4 itself is like super accurate, right? So unless you run validation on Coco dataset, you can't see it, at least in most cases. uh, Now you have or not rather pre, but optimization during training. So if you want to do FP16, there is something called mixed precision training, right? Or automatic mixed precision, AMP. So both TensorFlow and PyTorch support this, and you can pretty much do that. So in that case, when you go from FP32 to FP16, there is zero loss. Now the newest thing in the market, I would say, is quantization aware training, which TensorFlow supports. I'm not very sure if I think PyTorch supports with the latest TRT release, but TensorFlow definitely has this. You can actually do quantization aware training, where training with int8 is done together, right? So in that case, what you can do is you train with quantization aware training, you prune your model, you retrain it, and then you don't have to create that graph at the end that I spoke about, right? Post quantization aware training, you don't have to create that graph. Your model will already be int8 compatible. So yes, it does degrade your performance if it is post quantization, and it does not degrade your performance if you incorporate it during training.
Thanks a lot for the detailed answer. And yeah, quantized our training helps a lot in some scenarios. So the next question is Deepstream only applicable for computer vision application or other applications like NLP? Does it help over there also?
Okay, this is also a really great question, right? So far, Deepstream has been very focused on computer vision applications. But in the previous release, which is Deepstream 5.1, we did see a classifier for audios, right? For audio input. So there is slowly a shift happening to not shift, but rather incorporation of your NLP and NLP, ASR, and TTS, right? So eventually these things will come out in Deepstream as well. Since it wasn't there, I think it's not yet there. I would suggest looking at NVIDIA Nemo or NVIDIA Jarvis. Both of them kind of give you the kind of experience that you want, right? Accelerated output, but for NLP. So NVIDIA Nemo allows you to experiment like a researcher, and NVIDIA Jarvis is more production ready. So it kind of integrates RASA and punctuation capitalization, different language models. I think they have a language model for biomedical terms also, right? It's called Biomegatron, if I'm not wrong. So you can give that a shot as well.
Okay. Yeah, we have a next question. Like, can we just mention about the performance of DS in Jetson device? So Deepstream, how it improves in Jetson?
Okay, so if this is from a personal experience, right? I tried running CenterNet on a Nano, and it was terrible. I mean, we were just getting like 2 FPS out of it. Again, Jetson devices themselves are very, very, very underpowered. So don't expect to run like some 50, 60 streams on it or some very big models on it. That's not how you should be going about it. Jetson is an embedded platform. So before you deploy on it, you should try to do all the kinds of optimization that you can. So definitely Deepstream improves the performance on Jetson devices a lot. I definitely recommend using Deepstream. Now more detailed into what kind of performance you can get. If I can quickly open up
Could you
their
share your
page.
screen?
Yeah, that's exactly what I'm going to do. Yes, I've shared it.
Yeah.
Right. So actually, NVIDIA kind of gives you estimations here. If you're trying to run PeopleNet, which is their person detector network, you get around 11 FPS on a Nano. On a Xavier NX, if you run on the GPU of the NX, you can get 180 FPS. If you run on the deep learning accelerator, you can get like 58 FPS and so on. So this FPS is like pure performance benchmark. If you run with Deepstream, that involves decoding the input and showing on the screen and all of that, right? So you can consider a 10 to 15% reduction in performance, but also you can add a tracker and skip frames every 1 or 2 frames. I mean, skip every alternate frame or so, and increase that performance back to these numbers. But these give you a rough estimate of what kind of performance you can get.
Okay, thanks. And one more question, this out of the topic, but what is your take on OpenGL and other alternatives, DirectX?
Right. So, I mean, I think there are several alternatives out there. There's something called Chainer CV. There's OpenGL. There are several accelerators. Right. OpenCV itself has a deep learning. A deep neural network accelerator. So
Yeah,
there are a lot of packages out there that actually use GPU acceleration. Some of them use Cuda in the backend. You may not know, like like Blender and all of those applications. They use Cuda in the backend. OpenGL, yes, not associated to Cuda, and there are a few examples here and there where people have accelerated neural networks with OpenGL and stuff. And absolutely, why not, right? I mean, go for it if it's giving you better performance. But
yeah,
at least so far I haven't seen an OpenGL example which beats this kind of output. So
yeah. My question came from the point where we are too much dependent on NVIDIA. Thing, since they provide the entire technology stack, we have a lot of optimization. But some people might be having the hardware might be different. Like they might be using some different hardware. So in that scenario, they should be able to use the open source version, right? So that was the question coming from. So next question is: so is TensorRT the only reason you can run YOLO with that speed, or in parallel, or what is the other part of Deepstream which is mainly contributing to the higher FPS? So other than
uh,
inference,
so
what
I,
are the other things that helps?
so again, as I had mentioned, right, your bottlenecks pretty much happen at different parts of the application. So I guess if you can just pull in my screen again, I'll just go through that
Yeah,
architecture once. Right. Now here again, coming back here, right, you make your connection with your CPU, you decode on this on a CPU, right, again in a regular pipeline. uh, 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 as I said, decoding on a CPU is very intensive because you have to decode if your input is HD in size, you have to decode 1920 times 1080 times 3 number of pixels, so that you can run inference on it. So very slow process. Image processing, right? So scaling, developing, maybe they're not that they don't consume that much power, at least not on one stream. But when you run it in parallel, right, your CPU only has like 8 cores, 16 cores if you have like a really good CPU, maybe a Xeon, so you have even more cores to work with. But again, there is a limit to what you can do. In a GPU, the number of kernels you have are huge, right? Or the number of cores that you have are huge. So, a T4 has it in thousands, right? I think around 3,000 or 2,000 or something. If you see the latest 3090 RTX 3090, that has like insane amount of cores and more than 10,000 CUDA cores. So I'm not saying one core can do one task. It's that that's oversimplifying it. But again, GPUs are designed for images, right? So or the design for matrix operations, and these are matrix operations again. So again, comparing to a typical pipeline, you perform batching on a CPU, your inference is on a GPU, great. Your tracking might be on a GPU or CPU based on what you're using. Your visualization definitely CPU. Now the other problem is when you are pushing data onto the GPU, then again you're taking it out, again you're pushing data in, again you take it out. So that's where the bottleneck lies. The transaction between devices, between the IO transaction, that is slow. You can't keep doing it over and over. So if you put everything on the GPU, then absolutely, you don't need to do that transaction, right? As I said, C++ pointers, you have you know the memory location of where your data is. All your plugins can refer to the same memory location, that you don't have to keep making copies of this memory location and moving forward and forward, right? You just give it this memory address, like this is the data, do your action on it. Then the next plugin, again on that same memory address, this is the data, perform your action on it. So That's how basically Deepstream kind of optimizes it, and this is based on GStreamer. So again, it's not restricted to Deepstream, but currently Deepstream is the best thing out in the market. So I would suggest using this. But the crux of this is the GStreamer pipeline. So that's how it is designed. And if of course, if there is something similar out there, it might give you similar performance.
Thanks. So next question. How can we do tracking or add something to the algorithm on top of the pipeline? Can we mix Python and CPP in Deepstream?
Okay, wow. I would suggest to stick to one native language. It keeps things easy. If you are in Python, you can, of course, load a CPP module, parts of CPP code, right, with some form of acceleration. If you are in CPP, I think there are some methods to kind of get Python modules inside. I would strongly not suggest you do that, because whatever can be done in Python is also possible in C++. It's slightly tough, but it is possible, right? Again, but if you're on if you're on a time constraint, then there are definitely methods on this. You can personally ping me. It would be very it would be a long topic to take over here, so I won't take it up here, but then of course it's possible. And to the previous part of your question, I think it was something around tracking, right? Can you
So adding
how
customization on top of model.
how we can customize the tracker? Okay, so okay, that means how we can add our own custom tracker in the pipeline. So the NV tracker plugin is open source. You can actually plug in your own tracker into it and use it. Or if you want to use the tracker that is available, there is a very comprehensive config file that the tracker has. So that one of the trackers that NVIDIA provides is NVDCF, the DCF tracker, and it's pretty amazing. I mean, it integrates Kalman filters, it integrates Hog transforms, and it integrates a lot of things for you to kind of modulate the accuracy that you want. So you can use that as an out-of-the-box tracking service, or definitely, if you want to modify your own, open up the NV tracker plugin code, make changes to it, compile and execute. It should work.
Yeah, just to add on top of this question, not just tracker. If I want to add some custom logic on top of the model, is it possible to do that also on GPU with this NVIDIA Deepstream pipeline, or how is it?
Yeah, absolutely. I mean, as long as you can, as long as it is, as long as it can be accelerated, right? So, if your logic involves, let's say, writing a for loop and just checking what objects that are there, I mean, you're better off just writing pure CPP code. If it has more complex operations in it, maybe you want to do a search, or maybe you have some 10,000 outputs and then you want to kind of search in it, or perform some operations. Yes, parts of it can be accelerated with the GPU. So there's something called a Cuda kernel, right? So if you can represent your data in the form of a vector or a matrix, you can definitely accelerate it. So that's how it goes. If you can represent it matrix, go with the GPU.
Okay, thanks.
Does Deepstream support bias? Does Deepstream support bias towards a particular cloud service, or do we have APIs to help fit the pipeline? Okay, so I don't want to really get into the business aspect of it, right? I mean, NVIDIA might have tie-ups with Microsoft, or AWS may not be supporting some specific format. But think of it in the other way. They also let you define your own custom plugins to connect to whatever you want. So from an organizational point of view, at least where I work, we don't really use their Kafka plugins or their AWS integration, right? We have our own integration for it, and we've designed it ourselves. So it could be as simple as making an API call from your code, or it could be more complex as writing a plugin and pushing your data over there, and then your plugin pushes the data to the cloud. So again, you're free to architect the solution as and how you want it.
Okay, can you explain a little bit about SGIE, how back-to-back detector works?
Okay, so actually, Deepstream has this representation for its engine called a primary engine and secondary engine, right? So a primary engine is one that runs typically on the entire frame. your secondary engine is basically run behind the primary engine, right? So a good example of this is uh, you're detecting cars, and you want to classify them as hatchback, sedan, van, whatever, right? So in that case you can use the classifier as SGIE, and your primary detector or your primary, let's say, YOLO detector as the primary engine. There are also instances where you might want to use an object detector as a secondary engine. So I think NVIDIA has a good example of that. They detect license plates on the crop of the car. So you don't try to detect the license plate on the entire image, but rather on the crops of individual cars. So in that case, your object detector runs in the secondary mode. So secondary mode just allows you to define which primary engine you want to run, and on what class ID to run on. So it's like a standardization of stacking your models together.
Okay. There was one more question, like, does it, what all OS supports Deepstream? Well, it was a general question that came before. Does it support it all?
Linux. It's just Linux, unfortunately. So anything that is Linux based, Ubuntu, Fedora, rel based stuff, I mean, go for it. Linux is pretty much the only supported thing for Deepstream. If you want to use Triton Server without Deepstream, and if you want to use TensorRT, I think you can do it on Windows. But I personally suggest go with Linux. It's much more developer friendly. I know Windows is user friendly, but Linux is developer friendly.
Okay, thanks a lot. No, Navneet, would you like to ask something?
Okay, yeah. Thanks, Akash. Again, we have 5 minutes left. Hopefully, you can just guide us about how to get started with Deepstream and TensorRT and edge computing.
Absolutely. So I guess before I do that, thanks for having me. It's been an absolute pleasure, and I mean it's always interesting and fun to kind of share the knowledge that I have, right? So absolutely grateful
Great.
for that. In terms of roadmap, so NVIDIA does have a has a set of certifications. It's called the Deep Learning Institute. You can look it up, or you can ping me as well. I can help you with that. So they do have some curated certificates and workshops that help you kind of grasp these concepts and understand. So there are certifications for accelerating C and C++ code on GPUs, Python code on GPUs. There's Deepstream. There's recommender systems. There's a lot that you can learn from. It is not just restricted to to computer vision, but it's much more vast. So definitely you can look that up. And Deepstream also has I mean, NVIDIA also has this feature where you can request for a workshop. So whenever they have a GTC or some session like that, definitely you can have an instructor led workshop where someone kind of teaches you. And also, since I'm an ambassador, the whole idea is to kind of share the knowledge. So uh, 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 you know uh, I might have sessions later on once the situation kind of stabilizes. So you can definitely look that up. But yes, I think currently just go ahead on NVIDIA's Deep Learning Institute page and pick up the skills that you want.
Great. That's it. I think. Thank you, Akash. Thank you so much. Again, we have shared a lot of things. Hopefully, even I'm excited to try these things for myself, and it kind of got me curious to dig much deeper into the architecture, like how a GPU is working with the data stuff and all. And for the people who are watching this, you can find Akash easily on LinkedIn. You can just Google his name and you can find him, and you can reach out to him at any time. It's very helpful, and you can get guidance from him on your career learning path. And again, once again, thanks Akash for being here and sharing your knowledge and putting in your time and efforts to make this a great event. And
Thanks a lot, Akash.
yeah, again, please do join our meetup groups, AI Coimbatore Tensorflow. So we are planning for more such events in the coming days. Again, even if you wanted to share your experience, like also you can reach out to us. You can be a speaker for our event once your profile gets evaluated. So thank you. Take care. Stay
Yeah.
safe, and yeah, bye.
One small thing to add, please add your feedback so that we can improve upon on the upcoming sessions. And thanks a lot, Akash. That's it.
Thanks, guys.
Akash,
Thanks, everyone.
you want to give
I'm sorry.
do, do you have an end note? You want to say something?
I mean, just keep grinding. Keep grinding. Keep working hard. That's pretty much the
Okay.
only thing I tell everyone. So,
Great.
all right.
Thank you, man.
Cheers,
Thank
guys.
you. Bye.
Hope you all
Bye.
have a good evening. Bye bye.